Today's topic is going to be Infinium Best Practices. While this is geared somewhat towards labs or individuals who are newer towards the Infinium assay, it can also be a great refresher if you're planning on maybe ramping up your throughput or starting up your lab again after a temporary shutdown. This presentation is divided into two sections. First, we'll be discussing lab preparation and suggested standard operating procedures. Specifically, we'll get into laboratory space management and cleaning recommendations, equipment and instrument maintenance, record keeping, inventory management, and project management best practices. The second half of the presentation will go through specifics for the Infinium protocol best practices. The detailed steps of the Infinium protocol are shown on the left. We'll go through recommendations before you begin the assay, and then get into details for each step in the sample preparation steps and the BeadChip processing steps of the protocol. We'll also discuss QC and data management best practices, and you may notice that throughout the webinar, there's sort of a recurring theme that cleaner equipment can help produce cleaner data. So I encourage you to pay attention to that throughout the talk. All right, so beginning with laboratory preparation and suggested SOPs, we recommend setting yourself up for success by engineering a laboratory space that's specifically designed for processing the Infinium assay. You can physically separate your lab into two separate areas: a preamp area, where the activities leading up to the whole genome amplification will occur. This is day one of the protocol. And that can be, again, physically separated from the post-amp area of the lab, where everything from fragmentation onward will occur. You never want to share equipment between the preamp and post-amp areas. We recommend having separate sinks and water purification systems between these two areas, and storing supplies in the preamp area, transferring them to the post-amp as needed. The overall goal here is to eliminate the movement of people, supplies, and equipment from post-amp back into preamp. This helps reduce the likelihood that previously amplified DNA products will make their way back into the preamp area and risk contaminating future whole genome amplification runs. More specifically for your lab space, we suggest creating dedicated stations for each step of the protocol. This can help minimize cross-traffic within the lab space and also reduce confusion if you stock consumables that are used for each particular step at that dedicated station. Perform regular cleaning and room maintenance activities. Again, as I already mentioned, you want to eliminate or minimize the movement from the post-amp area to the preamp area. You don't want to share any equipment, and that includes lab coats, gloves, safety glasses, pipettes, centrifuges, heat blocks, heat sealers, right? We could go on. There's a lot of equipment in the Infinium assay. So you want to have separate sets between those two lab spaces. Store materials in the preamp area, and we suggest establishing a daily and weekly bleaching schedule. So specifically for how to clean your lab space, you can use 10% bleach solution on all lab surfaces, and we suggest cleaning them weekly with a higher frequency of cleaning on a daily basis for the typical hot spots or higher risk areas found in the lab. These are surfaces or handles that you might frequently touch with your gloves and are thus slightly more likely to be contaminated. But you should thoroughly clean all lab surfaces and instruments once a week with that 10% bleach. And anytime you do a bleach cleaning in the lab, make sure you allow time for the bleach vapors to dissipate before beginning any lab processes or handling any samples. For the instruments, the iScan, we recommend cleaning the BeadChip carriers and the iScan tray that comes out of the instrument periodically. Keeping the iScan clean is important for consistently obtaining high quality images. Now this is because dust particles or any residual buildup of the XC4 coating in the BeadChip carrier or the tray can actually prevent the BeadChips from laying flat in the scanner, which, as we'll discuss later, having the BeadChips lay flat is essential for allowing the scanner to establish the correct focal plane and get good clean images. We also recommend conducting an annual preventative maintenance service visit. For the Tecan, so this is the automated liquid handling robot that some labs have. It's an optional piece of equipment for higher throughput labs, so not everyone will have one of these. But if you do, have a Tecan, we recommend that you power cycle the system on a daily basis. This can just help make sure that the RAM is refreshed and keep the computer clean so it doesn't freeze up. So related to that, it's important to know the proper power cycle sequence for the Tecan and all your instruments in the lab, really. So if you're not sure what the proper power cycle sequence is, please just reach out to either your field service representative or give us a call at tech support, and we'll be happy to help you with that. For the Tecan, we recommend checking the system fluid level and the water circulator water level on a daily basis to make sure those have sufficient fluids. You can perform a tip wash on a daily basis with 5 mL of 10% bleach, and then a system wash before every time protocol is run on the Tecan. While you're doing the system wash, you want to check the lines, the fluidic lines that run from the syringe pumps to the tips of the Tecan, and make sure that you have a constant bubble-free stream of liquid. So you really are looking for any air bubbles you see in the lines. And if you see air bubbles, you should continue doing system washes until you don't see them. This can be a particular concern if the system has been idle for an extended period of time, such as after a lab shutdown. You might have to do more than the usual number of system washes in order to clear out the air bubbles. On a weekly basis, we recommend cleaning the outer surface of the tips. So the steps for how to do this in the software are shown on the slide. And then you can wipe the lower half of each tip with a Kim wipe soaked in ethanol. On an annual basis, you can perform the preventative maintenance service activities. You can reach out to us in tech support to get those scheduled. And annually, or anytime mold or bacterial growth is observed anywhere in the system, you'll want to perform the robot bleach wash. This can be done using 1 liter of 10% bleach solution. So in addition to performing the actual maintenance, it's important to keep records that the maintenance activities were done. We also recommend developing a system to keep track of the processing information that is recorded during processing the assay. If you have an organized system in place in the lab, that can really help expedite retrieving the records of what was done, and that can help with any troubleshooting should you run into any issues down the road. So really developing a system to organize all this information can be really helpful. For the maintenance activities, we suggest recording records of the preventative maintenance that was conducted and any service dates for your instruments if they required an engineer to come out and perform service. You can also record the first wash of the day for the Tecan, and anytime you run the robot QC test on the Tecan, you can record the results from that as well. We'll get into more details of the processing record keeping during the second half of the presentation, but to give you an overview of the types of information you'll need to develop a system for, we'll be collecting any reagent barcode information during the lab processing, so what lot numbers were used, and which samples or chips used which reagents. For the Hybe chamber, you'll want to be tracking which Hybe chamber was used, so you can label the Hybe chamber lid and base, and keep track of which BeadChips go in which Hybe chamber, and which positions within the Hybe chamber they're located in. The T-flow apparatus, which is where the XStain portion of the protocol takes place, you'll want to be tracking where each BeadChip is located on the T-flow. There's many spots that they can go in, but you'll want to keep track of which position each BeadChip was placed in, and any results from the temperature checks conducted with the probe prior to beginning XStain. For inventory management best practices, we recommend using a first-in, first-out system for reagents and consumables. You can label any consumables that you receive with the date that they arrive, and any bulk reagents can be labeled with the date of first use. This can help you rotate through your stock and avoid using any expired reagents, which might perform unpredictably. So you want to try to avoid that if possible. DMAPs are electronic files that are used by the scanner to know where each bead has been randomly assigned a position on the BeadChip. So these files are necessary for scanning, but you'll want to download them as soon after receiving the shipment rather than waiting until when you're doing the scan. This is important so that if you ever have an issue downloading the DMAP file, my dog really wants to agree with this point. I'm not sure if you can hear him barking, but it's really important to download your DMAP soon after receiving the shipment. You can store them in a backed up location if possible. And if you have any issues or want more advice on downloading DMAPs, you can see the tips and tricks for downloading DMAPs using the Decode file client that's available on our website. Another recommendation for inventory management is to develop a lot control system for any user-supplied reagents. So since you're preparing these reagents yourself, they won't come with a barcode or a pre-assigned lot number. So it's up to you to develop a system to generate that number. The user-supplied reagents in the Infinium assay are formamide EDTA and NaOH. We recommend labeling them with the date that the reagent was prepared and the initial of the person who prepared them. So for example, if today's date is 200423 and my initials are SS, I might mark that lot of reagents with that unique lot number. You can generate the user-supplied reagents in large batches and then aliquot them and store them at the correct temperature, which we'll get into in more detail later in the talk. Another suggestion relating to inventory management is to make sure you're setting yourself up for success by initially ordering a kit size that is appropriate to your sample processing batch size. So you'll notice on the Illumina website when you go to purchase a kit that there are many different sizes you can choose. Rather than attempting to split a large kit, if you're only processing a small number of samples at a time, working in lower throughput, we recommend that you order the smallest size kit possible. Kits are not intended to be split, and this might result in reagent shortfall. And since many of the reagents cannot go through freeze-thaw cycles, it's really best to try to just order the kit size that matches your processing batch size. For project management best practices, we recommend you track project QC metrics and processing control performance. If you're tracking these regularly, both the call rate data, the behavior of the built-in controls, and any intensity data, that can help you catch and address problems early on. You'll want to look for any patterns, and if you want any assistance with troubleshooting, should you encounter any issues or notice any abnormalities as you're tracking your QC results, just reach out to us in tech support. We'd be happy to help you with identifying any possible root causes and making suggested corrective actions. Another tip for project management is that you can include some positive control samples as a processing check. So these would be samples where you're known to have good quality DNA, and you can therefore expect good quality results if the processing goes correctly. You can put these in the plate randomly. You can also include a tracking control for plate orientation that would allow you to determine if the plate has maybe been rotated, 180 degrees or something like that during processing. Next, I want to discuss the resources and documentation. So we recommend using the most updated resources and documentation, which can be found on the Illumina.com website. Specifically, you can search for the name of the BeadChip you're processing, plus the word support. And if you type that into the search bar at the top of the Illumina.com website, you'll find the support resources that are appropriate for that particular BeadChip. So for example, if I was running GSA chips, I could search for global screening array support in that search bar, and that would bring me to the support resources page that's shown on the left side of the slide here. You can see that this includes sections for documentation, product files, and product information. And if you were to scroll further down on the page, you would get to the training section, which is shown on the right of the slide. This contains many useful training resources that are appropriate for the particular BeadChip support page that you're looking at. So if you're doing a methylation epic trick, there'll be training resources that are specific to the methylation assay. And I also want to bring your attention to the View All button there next to the training. There's just 3 trainings that are highlighted, but we have many more resources available on the support site. So I do encourage you to have a look at those as you're getting going with the Infinium assay. I also want to point out that since there are many types of BeadChips, sometimes with similar names, and then within each type of BeadChip, there's different versions of the BeadChip. So the global screening array, for example, we have version 1, version 2, version 3. You want to make sure you're using the correct resources for the BeadChip type and the BeadChip version that's being processed. To look at a little more detail at these support resources, in the documentation section, that's where you'll find the most up-to-date assay reference guide. So this is the protocol for the Infinium assay. And there's different reference guides for the different assays, for the different flavors of BeadChip, if you will. So you'll want to make sure you're using the correct assay reference guide, which again can be found on that support page by looking up the BeadChip name. You'll also find the lab setup and procedures guide listed under this documentation section. And this has many of the best practices that we're talking about today. So if you prefer a written format of these best practices, highly encourage you to have a look at the lab setup and procedures guide. The product files indicated in green here include the manifest file, cluster file, and the LIMS product descriptor file. We often get questions in tech support about how can I tell if a certain SNP is on a chip, or where is the list of SNPs for this BeadChip? And the answer to those questions, we would refer you to the manifest file for the BeadChip in question. So this can be downloaded from the product file section of that BeadChip support page. The purple box is indicating the support file section. So there's actually a myriad of support files for every BeadChip. My favorite one personally is the loci name to RSID conversion file. And this is useful if you want to report your data in terms of the RSIDs from the dbSNP database, as opposed to with the loci names. You can import that file into Genome Studio. There's also mapping comments, population reports, if you're curious about minor allele frequencies. There's demo data, so a Genome Studio project that's made for that particular BeadChip. So if you're just getting started and you want to know what the data is going to look like when you're done processing, you can get a head start on what your analysis pipeline will look like by downloading the demo data and playing around with that in Genome Studio. Our data management best practice recommendations are that you keep the BeadChip images, the JPEGs, the DMAP file, so that's the decode file, and the physical BeadChip itself until QC is completed. That's because if you want to rescan the BeadChip, you can do so, and maybe you'll get a different result if there had been an issue with the actual scanner itself. So we do recommend you hold on to those until you're sure that you have good data. However, you should permanently archive the intensity data files. So those are the IDATs, and that's the raw data generated by the scanner. You might also want to consider saving a copy of the relevant product files for the project, so the manifest and the cluster file, along with the IDATs, just so you don't have to go tracking those down later should you ever want to recreate your Genome Studio project or use them for some other purpose in analysis. All right, so that wraps up the first portion of the presentation, and we'll now be discussing the specific Infinium protocol best practices. These are geared more towards bench work in the lab. Before you begin, you'll probably already have a lot of these steps completed if you've followed the recommended best practices discussed earlier in the presentation. But you'll want to make sure you have the most up-to-date protocol on hand, which again is available from that support webpage. Make sure your DMAPs are downloaded and available. And make sure all user-supplied reagents are prepared and that no reagents, user-supplied, or consumables are expired. Select the samples you want to be processing and include any controls if you want to include controls, and you can prepare a sample sheet if you would like. Make sure you have the lab tracking forms ready to record the processing data, and of course make sure you're wearing appropriate PPE, so gloves, lab coat, etc., and practice good lab hygiene. In general, the recommendations that apply throughout the protocol relating to reagents are that you should pull the reagents in advance of when they're needed so that you can be sure that they're fully thawed and you don't have to extend or delay incubation times. Make sure you completely thaw and briefly vortex all reagents to ensure efficient mixing. And then you can give them a quick spin down or just flick it to get the liquid out of the cap before opening the tube. You want to avoid multiple freeze-thaw cycles of the reagents and do not mix or combine reagents from different lots. RA1 and XT4 are two particular reagents that have special handling instructions, and we'll go through those when we get to that point in the protocol when those reagents are used. For the user-supplied reagents, an AOH and formamide EDTA, we do recommend making these up in large batches and then making aliquots. So for 0.1 normal NaOH, we suggest 50 ml aliquots, and those can be stored for up to 6 months at 4 degrees. Or you can dilute weekly from 1 normal or 10 normal stock, depending on your throughput needs. For the 95% formamide 1 millimolar EDTA, again, we recommend making a large batch and then storing 15 ml aliquots. In particular, for formamide EDTA, we recommend using a very tightly sealing tube because formamide is sensitive to degradation from the air, which is why we recommend that you discard the aliquots after use. So you don't want to be reusing formamide. Make a large batch and put them in tightly stored tubes. They can be stored for up to 6 months at -20. For general processing best practices, you'll want to stage the plates, kind of stagger them as you're going through in order to keep incubation times consistent from plate to plate. We recommend orienting the cap mat properly each time, making sure A1 is at A1 to avoid the risk of cross-sample contamination. The cooling steps that are noted in the protocol are important for data consistency, so we do recommend carrying them out as directed in the protocol. And when you're getting ready to scan, go ahead and turn on your scanner at least 30 minutes before putting the BeadChips in, and this can give the laser time to warm up. For project tracking, I know we've discussed this extensively for how to set up a system in your lab, but some specifics of things you want to be tracking while you're processing the assay are to make sure you're recording the barcodes for all the reagents that are used. If you have a barcode scanner, it's super easy. You can also just jot down the number that's located underneath the barcode if you don't have a barcode scanner. You want to keep all the plates in the same order as you're going through the assay and make a note of which order the plates are in on the deck, which position they're in if you're using a Tecan. You can record all this information in a lab tracking form. So any critical steps, incubation times, temperatures, where things are in the T-flow, how plates are batched, all of this information is really useful to record on a lab tracking form and provide that to a project manager along with the data when you're done processing the assay. And lab tracking forms can obviously be paper or electronic. We have some available on our website, or if you'd prefer to develop your own, that's fine. Just be sure in one way or another that you're recording this information as you're processing. Okay, so as we get into each individual step, I first wanted to give an overview of the Infinium assay in general. So it's a 3-day process, which consists of sample preparation that occurs on a plate level, a 96-well plate, and then day 3 includes the BeadChip processing that happens on the physical BeadChip itself. So to start with, you're going to quantify the DNA, and you're targeting a concentration of about 50 nanograms per microliter. Once you have normalized your samples to that concentration, you can start the whole genome amplification process. And this marks day 1 of the Infinium assay. The amplification is an overnight process, and you'll begin day 2 conducting the fragmentation to chop the DNA up into smaller pieces, precipitate it to purify out any enzymes, and then resuspend it in a buffer that's appropriate for hybridization. When the sample is hybridized to the BeadChip, that then marks the beginning of the BeadChip processing, so from day 3. And this is really the crux of the assay where the single base extension chemistry and then the staining occurs. So we call these 2 extension and staining steps together XStain, and that happens on the T-flow apparatus that we'll be talking about extensively. The last step is imaging, where you'll take your BeadChips on that blue carrier, or some people have black carriers, and along with those DMAPs, the electronic files, the map of where the beads are, you'll put that into the scanner and you'll get out your IDATs. That's your raw data. All right, so for the quantification, the best practices for that step are that we recommend using a fluorometric method, such as qubit or picogreen, in order to determine your DNA quantity. Spectrophotometers, while great for determining sample purity, aren't specific for double-stranded DNA, and sometimes this can result in an overestimation of the sample input. So we really do recommend that you use a double-stranded DNA-specific quantification method, such as a fluorometric method. And again, you're targeting an input concentration of 50 nanograms per microliter. You can also include some tips for detecting contamination. If you mark the gender of the samples on the sample sheet or use the gender estimation algorithm in Genome Studio, that can help you determine if you're getting data from the sex chromosomes consistent with the expected sex of the sample. You can also include replicates in the sample sheet for replicate calculation. So once you've got your normalized quantified DNA, you can start with the optimized whole genome amplification reaction. This amplification reaction has a reduced GC bias, and it provides up to 1,000-fold amplification of your starting materials with no appreciable allelic partiality. So the best practices for amplification are to really focus on the quality and quantity of your input DNA. It's a fairly robust amplification process, so if you can really focus on the quality and quantity of the input DNA, you'll likely be very successful. You can vortex or spin or flick the reagents prior to use, just to ensure that the reagents are well mixed. And you'll want to use fresh, properly prepared NaOH. Again, we talked about that large aliquoted batch that's stored at 4 degrees. This is important because the pH of NaOH needs to be at the correct level in order to denature the DNA during the amplification reaction. We also recommend that you mark the cap mat orientation to make sure, again, A1 is over well A1 to prevent cross-sample contamination. And lastly, just make sure that your hive oven is set to the correct temperature, 37 degrees, as stated in the protocol. After the overnight amplification, you'll do fragmentation, and the purpose of this step is to chop up the DNA into smaller pieces, and this provides better access to the majority of the genome. It's a robust endpoint fragmentation that results in fragment sizes of about 300 to 600 base pairs. So these will hybridize better to the BeadChip that has those 50 base pair probes. For best practices in fragmentation, we recommend that you check the temperature on the Hive X. This is an enzymatic process, and the enzyme is active at 37 degrees. The next step is precipitation. The purpose of this is to purify the DNA samples and remove any enzymes or other proteins and materials from the earlier steps in the protocol. For best practices, we recommend immediately removing the plate from the centrifuge after it's done spinning. If you're there waiting for the centrifuge to stop as soon as it beeps, that can help avoid dislodging the pellet and accidentally discarding the pellet. So you don't want it to be sitting there in the supernatant after it's been spun down. You can visually check for the blue pellet of DNA by looking through the well of the plate. It should be visible through the plastic. And when you're decanting the liquid or the supernatant, use a firm smackdown technique. So what we mean by this is that you'll abruptly invert the plate and firmly smack it down on a paper towel or like an absorbent baby diaper type material. This can help avoid cross-sample contamination if you do this firmly, and then once the plate is inverted, leave it inverted. So you don't need to be peeking and tipping it up. So you don't want the liquid to flow between the wells. So after the plate's inverted, leave it inverted. Avoid over drying the pellets because this can make them difficult to fully resuspend. Resuspension occurs with the hybridization buffer, RA1. So this is one of the 2 reagents that I said earlier has special handling instructions. Although like all reagents, it's important to make sure it's fully in solution. For RA1, it's especially critical to make sure that you're using fresh RA1. Only pour out the amount that's needed for each step and don't pour it back into the bottle. Discard any RA1 that has been exposed to air for an extended period of time. The reason for this is that RA1 contains formamide, and air can actually oxidize the formamide into formic acid, which will make it less effective. Store RA1 at -20 degrees between days 2 and 3 of the protocol. So this reagent is used at 2 points in the Infinium assay, and you should store it at -20 in between uses. RA1 contains formamide, as I said, and that's an aliphatic amide, and it's probably a reproductive toxin. So please handle it with care and use appropriate PPE. Once your DNA has been resuspended, it's then time to hybridize it to the BeadChips. So the purpose of this is to allow your genomic DNA to find any complementary probes on the array and bind to them. The conditions for hybridization are very important for success of the assay, and it requires a temperature and humidity-controlled environment. So starting from this point in the protocol, we're going to spend a little bit more time discussing the equipment that's used and how you can check to make sure it's in good working condition. Before you hybridize your DNA to the BeadChip, you want to make sure that DMAP is available. Again, have that downloaded. Once your sample is loaded onto the chip, it's kind of the point of no return in terms of choosing to use a different chip where you do have a DMAP or something like that. So make sure your DMAP is already downloaded. Carefully inspect the hide chambers and gaskets. I'll talk about this a little bit more on the next slide. And once you've added the humidifying buffer, make sure that you place the BeadChips in that hide chamber within an hour in order to prevent evaporation. Open the foil BeadChip pouch only when you're ready to use the BeadChip and load the sample onto it. So from the moment you open that foil pouch until you have XC4 coating on the BeadChip at the very end of the protocol, your mission is to prevent the BeadChip from drying out. So this is something we'll talk about over and over again for the rest of the presentation here. You want to avoid the BeadChip from drying out. So one of the ways you can prevent that is only opening that foil pouch when you're ready to load the chip. Handle the BeadChips by the edges and the barcode as shown in the image at the bottom of the slide. This can help you avoid getting any fingerprints on the sample region, which can compromise data quality. If you're loading the BeadChip manually, be sure to avoid injecting any air bubbles into the sample loading area by putting the pipette tip down all the way into the sample port before beginning to dispense the liquid from your pipette. If you're using a Tecan for automated loading of the BeadChips, make sure you use the tip guide that's appropriate for that BeadChip. The tip guide helps funnel the Tecan's tip into the exact precise location on the BeadChip in order to load the samples. After you're done loading, do a quick visual check to look for the sample overfill bolus at the loading ports. This overfill bolus helps ensure that the arrays don't dry out during the overnight hybridization. You should also be recording the positions within the hide chamber and which hide chamber is used. And lastly, you can check the hide oven temperature. Again, we want to provide a temperature and humidity controlled environment for hybridization. The hide chamber is a piece of equipment that's essential for maintaining the correct humidity. You can label the hide chamber base and the lid as a pair and keep them together. Inspect the hide chamber regularly to check that the clips and the feet don't have any broken or loose components. You need it to be sealing tightly in order to keep that humidity in. Inspect the hide chamber gaskets for brittleness or tears on a regular basis. So this is the orange gasket that goes in between the lid and the base of the hide chamber. To check the gasket, what you can do is fold it in half, and then on the outer edge of that fold, look really carefully for any hairline, little cracks, or any signs of like wearing rubber. And if you do detect that, we recommend replacing it. These do wear out over time, so if you've been using the same gaskets for years and years, it might be time to replace them. And I've mentioned this several times now, but please make sure you're tracking where the BeadChips are in each hide chamber. After hybridization, you'll have to remove the hide seal off the BeadChip and then wash the BeadChips. Make sure that you place the BeadChip in PB1 immediately after removing the hide seal. Again, we don't want the BeadChips to dry out. If it does happen that you have some seal residue, some sticky material remaining on the BeadChip, you can remove that while the BeadChip is submerged under PB1 using a pipette tip. But again, you don't want to let the BeadChip dry out, so make sure you're doing that under PB1 if it's necessary. For washing the BeadChips, break the surface of the liquid line when dunking the wash rack up and down, so you want to make sure you're coming up high enough to break the surface and then going back down. Replace the PB1 and wash 1 after every 12 BeadChips. The flow-through chambers refer to the glass back plate, the BeadChip itself, the spacers that goes in between them, and then the clamps. So together these are assembled into something we call the flow-through chamber. And it's called that because the reagents flow through this during XStain. Proper assembly of the flow-through chamber is really important to generate the capillary gap that these extension and staining reagents will be flowing through. So there's step-by-step images in the assay reference guide, some of which are shown on the left side here. But it's really helpful, I think, to have a look at the pictures for how to properly assemble the T-flow chamber. You're going to want to make sure you're using the correct hardware for the assay that you're processing. The Infinium assay has a couple of different variations. So there's the HD and the LCG and the XT assays. These use different hardware. So the glass back plate is actually a different size for these different assays. So this is why it's important you know what type of bead chip you're using and that you're using the correct reference guide and hardware for that assay. Another extremely important point is that you're using clean glass back plates. We'll talk about this in more detail shortly, but this is a key success driver for the Infinium assay, the cleanliness of the glass back plates that you use. For example, in assembling the T-flow chamber, you'll want to place the clamps in a consistent location as described in the reference guide. Some labs choose to mark the correct clamp position on the alignment fixture with a piece of lab tape so that you can tell how far up and down the bead chip the clamp should be placed. For the spacers, the spacer is the clear piece of plastic. When you receive the spacers, they'll be both clear and white. The white plastic is just a backing. That's not the actual spacer, and you don't want to use that. Make sure you're using the clear part of the plastic. Trim the spacers using a well-functioning pair of scissors. The spacer alignment is really important for getting good results, and you want them to be on the outer edge of the bead chip and parallel to each other, not deviating into the sample area. This can actually cause problems during scanning if the spacer is misaligned and protruding into the sample area, because the scanner will incorrectly assume that that's the edge of the bead chip and it'll misalign the DMAP, causing issues for registration. So you want to make sure that the spacers are correctly aligned and that you're using a good functioning pair of scissors that actually cuts the plastic rather than pulling on it or kind of mashing it. So make sure your equipment is in good functioning order. More details on glass back plate best practices. These are detailed in the Infinium assay setup and procedures guide, but you'll want to soak the glass back plates in a prepared 1% Alkanox bath immediately after disassembling the flow-through chambers. So after you're done with the XStain, you want to get those glass back plates into the Alkanox bath immediately. This prevents the reagents from drying on the glass back plates, which makes them very hard to clean. You should do a 10% bleach cleaning of the glass back plates every 7 uses. This is a recommendation that can really help reduce the background in the assay, because dirty glass can cause an elevated level of background noise and poor performance. Some users that are really trying to minimize the background noise, if they're doing CNV analysis or something like that, where it's more sensitive to any background noise, they'll actually do the bleach cleaning after every single use. So if you're looking to improve the quality of your data, one recommendation is to do a really good job of cleaning your glass back plates and do a frequent bleach cleaning. Additionally, you want to inspect the glass back plates before each use and replace them if they're damaged. Some examples will be shown in the next slide. As I mentioned, there's different types of glass back plates for the different types of Infinium assay. We recommend storing them on separate racks that are labeled for either HD assay, LCG, or XT if your lab is processing multiple types of Infinium assays. This can reduce the risk of using the wrong glass for the assay. Additionally, you'll want to store them diagonally in a plastic rack to avoid nicking or cracking the glass. Some examples of reasons why you'd want to replace the glass back plates is if you notice that there's any chips in the trough area that forms the reservoir, or if there's any significant chip at all in the glass that could cause an injury, such as a cut when the glass is being handled or washed. If the glass is cracked, it's possible that it might break during XStain because it's going to be placed on this heated T-flow. So that would be grounds for a replacement, along with any significant scratches on the surface of the glass back plate that faces the array. So when you're making that sandwich of the flow-through chamber, the side of the glass that contacts the array should be as clean and scratch-free as possible. You don't need to replace it if there's scratches on the opposite side of the glass that's not in contact with the array. All right, so now that we've covered some of the equipment checks that you want to do, we now talk about XStain. So again, that's the single base extension and then the subsequent staining of that extended base. The extension adds a single ddNTP nucleotide to the last base of the probe. And which nucleotide gets added is based off of your genomic DNA template that's been hybridized to the BeadChip. A and T are labeled with DNP, and C and G are labeled with biotin. So in the subsequent staining step, whether it's labeled with DNP or biotin will determine whether it gets stained red or green. And then the fluorescence scanning detection will determine which base was added during extension. The best practices for XStain are to briefly vortex all the reagents before use, and again, give them a quick spin or flick them down to make sure there's no liquid in the caps. These are both temperature-sensitive chemical reactions, so that ensuring that the T-flow is at the correct temperature and that it's consistent across the unit is very important for successful XStain. You can use the Illumina provided temperature probe in order to check this. Another recommendation is to degas the T-flow before every time you use it. So every time you do XStain, you need to degas the T-flow. And I'll explain what I mean by that in just another minute. You'll also want to regularly check the water level in the water circulator to make sure that the heating element is fully submerged. This can make sure that the water that's flowing through the T-flow is able to be warmed to make sure that these reactions are happening at the correct temperature. Again, you'll want to track the T-flow position of where each BeadChip is put in the T-flow. I've already discussed this, but meticulous cleaning of the glass back plates is very important for successful results from XStain, as is correct assembly of the T-flow chamber. You'll want to disassemble the flow-through chamber immediately after XStain. If you're using a Tecan or an automated liquid handling robot, it's best practice to make sure you're double checking the deck setup prior to starting each protocol. So you just want to make sure what you're seeing in real life on the deck matches what the software is directing you to set up the deck position. You can also double check to make sure that the plates are seated well and not tipped up on any pins. To check that the robot properly executed each task, we recommend doing a quick visual check of the remaining reagent volumes after the run is complete. This can tell you if there's no reagent left in the tube, it's possible that the last few samples processed might not have received that reagent, and that's something you would want to note in your lab tracking form. Alternatively, if it looks like none of the reagent has been used, that would be also cause for concern, and you would want to make sure that it was put in the correct position on the deck and so forth. For the Infinium XT assay, we actually recommend that you use a serological pipette to measure the volumes of reagents that are needed, rather than relying on lines on those reagent troughs for the fill volume. This can help ensure you don't run out of reagents. The most important key for success, whether you're doing the automated protocol or manually, is to make sure that you degas the T-flow properly. Again, this needs to be done every time you run XStain. The purpose of degassing the T-flow is to make sure that there's no air bubbles that would adversely affect the temperature of a certain region of the T-flow. This black metal part of the T-flow is actually hollow and hot water is flowing through it. This is what gets the metal to be at 44 degrees Celsius, and therefore the BeadChip that's in contact with that surface during extension and staining reactions to be at the appropriate temperature. So if there's any air bubbles next to a region where the BeadChip is seated, this could result at the XStain reactions not occurring at the appropriate temperature. So you really want to remove all of the gas, all of the air out of that T-flow. If you imagine boiling a pot of water on the stove, you'll know that as the water gets hotter and hotter, more and more bubbles are formed. So it's important that you don't do this degassing process until after the water is already warmed up. Otherwise, new bubbles will just be created. So you want to do this when the temperature in the water circulator has almost reached 44 degrees Celsius. And this is a bit of a physical step. The T-flow apparatus can be a bit heavy. So if you don't feel comfortable doing these manipulations yourself, we recommend you talk to those your other lab partners and see if anyone else is comfortable doing this. because it's really not something to be shy about. You really need to give it a good shake and feel comfortable fully manipulating the T-flow. All right, so the step-by-steps of how to degas the T-flow are to separate that black heat exchange unit away from the white reagent pan. If you haven't been doing this on a regular basis, you might need to soak it in order to get them to separate. But anyways, you pull up on the heat exchanger and turn it so that the tubing's at the bottom. So if you imagine having X-ray vision and trying to visualize these air bubbles in this black box, you'll want to give it a little shake to loosen the bubbles and imagine them flowing up towards the ceiling. And then you're going to go through a series of 90-degree turns in order to push those bubbles that are rising up towards the ceiling up and out the tubing, so those waistline tubings. So you start with the tubes at the bottom and then do a series of 90-degree counterclockwise turns. You can almost imagine you're driving a car and making a left-hand turn. The T-flow should be perpendicular to the floor. So you can do this series of turns and manipulations 3 times or until you can no longer hear any bubbles in the T-flow when you shake it. Once you've removed all the air bubbles, use a Kim wipe and lab-grade water to wipe clean the top of the reagent pan and the bottom of the heat exchanger before putting them back together. There's a little pin, so you need to make sure that you seat the T-flow back on the reagent pan flush. If you're using a Tecan, make sure that you return the T-flow to the exact proper deck position. The robot doesn't know where exactly the T-flow is, so it's really on you to make sure that the T-flow, when it goes to dispense the XStain reagents, that you've lined up that T-flow exactly where it's expecting it to be. Some recommendations if you're doing XStain manually, as far as dispensing the reagents, make sure that the pipette tip is not contacting the surface of the BeadChip. Instead, the pipette tip should rest on the upper center side of the T-flow, of the flow-through chamber. So this is that glass back plate slanted reservoir side. Dispense the reagents slow and steady to avoid making any turbulence when you're dispensing. Start the timer when you add reagents to the first BeadChip and proceed in order. Change the tip between reagents. And we suggest using the experienced user card checklist in order to keep track of the steps, because several of them need to be repeated, and it's just easier if you're not trying to keep track of that in your head. Try to avoid injecting any air bubbles when you're pipetting the liquids into the reagent reservoirs. And disassemble the chambers immediately after you're done with XStain, as we've discussed. Once you're done with XStain, it'll be time to wash and coat the BeadChips. And again, you'll want to disassemble those flow-through chambers promptly and use the provided dismantling tool in order to avoid chipping and damaging those glass back plates. Immediately submerge the BeadChips in fresh PV1 in the wash dish. Again, we don't want to let the BeadChips dry out, and they still aren't safe until they're coated with XC4. For the XC4, before you use it for the first time, it needs to be diluted with ethanol. So you can add 330 mils of ethanol and vigorously shake it to make sure that you fully dilute the XC4 stock. You can store both the undiluted stock and the diluted XC4 at room temperature, but make sure you label with your initials and the date when the ethanol is added. This makes sure that everyone else in the lab knows that the ethanol has already been added, so it doesn't happen twice. Diluted XC4 can be reused up to 6 times over a 2-week period for a maximum of 48 BeadChips. For imaging, so the purpose of this step is to measure the fluorescent intensity on the eye scan. And again, this will help us distinguish whether it's green, red, or both fluorescence coming from the probes, and therefore the genotype of your sample. Turn on the scanner at least 30 minutes before use to allow the lasers to warm up. Make sure that the BeadChips are seated flat in the carrier and that the carrier is flat in the iScan tray. We talked about this a bit earlier with the iScan maintenance. You can also wipe the backs and the sides of the BeadChip with ethanol in order to remove excess XC4. Again, excess XC4 can interfere with the focusing process, but make sure you're only wiping the back and the sides. You don't want to wipe the front of the BeadChip where the sample area is. After you're done scanning, you can keep the BeadChips in a dark, dust-free storage location in case they need to be rescanned later. All right, with that, that concludes our discussion of the best practices for the Infinium protocol. To recap, we suggest that you check the DNA input quality and use a fluorometric method in order to quantify specifically double-stranded DNA. Separate your lab into pre-amp and post-amp areas, and make sure you're preparing your user-supplied reagents like NaOH correctly and making large batches that are then aliquoted. For the precipitation step, be sure to remove the plate promptly when the centrifuge is done. Check for the pallet by looking through the plastic and use the smackdown technique. Avoid turning the plate over after it's been inverted until the plate is dry. For resuspension, make sure you're using fresh RI1. Remember, we talked about how that reagent is sensitive to the air. And the hybridization, for all the BeadChip processing steps, you really want to make sure that the BeadChips don't dry out. So check the Hybe chamber equipment and your Hybe oven temperature to get that humidified, temperature-controlled environment. For XStain, we talked about the key success points of having a correctly assembled flow-through chamber and using clean glass back plates, as well as making sure that every time you do XStain that you're degassing the T-flow properly to make sure there's no air bubbles that could affect the temperature during the XStain. For imaging, seat the BeadChips flat in the carrier and you can wipe off any excess XC4 from the back of the BeadChips using ethanol. So to conclude, overall, we talked about the general laboratory best practices, so creating a dedicated laboratory space for processing the Infinium assay and proper cleaning recommendations. We talked about equipment management as well as inventory and reagent management best practices. For the wet lab work that occurs for the Infinium protocol, we discussed the quality of the input DNA, made some processing recommendations, talked about reagent use and sample tracking, as well as best practices when using the Tecan, how to degas the T-flow, and emphasize the importance of using clean glass back plates. We also mentioned some project and data management best practices. Some resources for your use, we recommend looking at the Infinium support page on the Illumina website. And this is where you can find the Infinium assay lab setup and procedures guide, the specific assay protocol guides for each Infinium assay. You can also find the system guides for the iScan and NextSeq scanners. Additionally, there's a lot of training resources. There's online trainings and links to other webinars. A great next one, if you're still getting used to the Infinium assay and how to evaluate the data quality, is to check out the online training for evaluation of Infinium genotyping assay controls. These are built into the assay. There's also many technical bulletins that are definitely worth a good read. So how to improve Infinium data using updated glass back plate care recommendations. There's tips and tricks for downloading DMAPs, proper care of the Tecan robot fluidics, and recommendations for XC4 reagent use and storage.